Hello students, today we will discuss one example of uniform circular motion, and that is conical pendulum. It is the best example of uniform circular motion. You know the pendulum. A point mass attached with a string. This string is long string, it is massless, and one peculiarity is that it is inextensible and it is attached to a rigid support. Then this system is called as a pendulum. If it is made to vibrate in this way with a very small amplitude along its mean position, then it is called as a simple pendulum. This you know. But if this string is made to revolve along right circular cone with vertical axis and point mass performs horizontal circular motion, then that system is called as a conical pendulum. So I try to demonstrate that simple point here. Suppose this is practically we have a thread as a string and point mass I have taken it as a in the form of a cubical mass. If it is made to oscillate in this way, then it is a simple pendulum. But if it is made to revolve in along the right circular cone with vertical axis, then here mass performs horizontal circular motion. Then this system is called as conical pendulum. So I can draw it in the diagram in this way. Suppose this is a rigid support. Support is rigid and this is a point mass. This is the string. This original position of string acts as a vertical axis and the mass is vibrated, mass is revolved in horizontal circle in this way. Suppose it is in anti-clockwise here direction, and cone structure or cone shape is traced by the string can be shown in this way. Simply you can here imagine the cone. Also you can perform the simple experiment to have idea about the conical pendulum in this way. So this one is the axis. This axis is vertical, but the plane of motion of particle is horizontal plane. Then such system is called as a conical pendulum. Now this horizontal circular motion we consider it as uniform circular motion, and for the uniform circular motion number of terms are related. First is angular velocity, then period of uniform circular motion, frequency of uniform circular motion, and velocity of the particle in the circular path. We have to write various relations and derive some relations for these terms which are related to uniform circular motion by considering this string mass system, that means a conical pendulum. So for that, here the diagram can be shown. Here again there is a rigid support. The same system I show here like this. A is a point at which the one end of string is attached. One of the position of a particle in horizontal circle is shown by B. Here particle is shown at a certain position B. Then its circular path also can be shown in the diagram. The horizontal circular path. Then center of circle is C. Here CB represents the radius of circular path. Here AC is the vertical axis along which the cone is traced. Here the semi-vertical angle is shown by theta, or it is the angle made by one of the positions of a string with vertical. This theta. Now we can write here the description for the figure. Here mass, tiny mass is taken, but it is having certain mass. It is mass of the point particle or particle. That particle here we call as a bomb. It is very small particle. Now L is the length of string. Then from geometry of figure we write R is radius of circular path. It can be BC. It is equal to L sin theta. The distance from the point of suspension and center of circular path is AC. It is L cos theta. Here simple geometry is there. Now in this situation, in this system, here for this point mass, weight can be shown vertically downward. Is vertically downward. Is exactly vertically downward is mg. Now along the string there is one force due to elasticity here. It is tension in the string. T0 is representing here a force along the string, and it is called as tension in the string. Now this tension is resolved into two components. One is T0 cos theta, other is T0 sin theta. These components can be shown in the figure like this. Here vertically upward component T0 shown here, vertically upward component. Here from figure it is theta angle, is T0 cos theta, and horizontal component is along the radius, it is T0 sin theta. Now from figure we can observe T0 cos theta is balanced by the weight. This is equation number 1. Now T0 sin theta is along the radius and directed towards the center. Therefore, it provides the necessary centripetal force. Here, centripetal force we write in terms of angular velocity. It is mr omega square, where omega is angular velocity for the particle or tiny mass, r is radius, you know. So here from these two relations we can write here sin theta upon cos theta is equal to, means dividing equation 2 by equation 1, we write r omega square upon g. This one is the third equation. Now from this relation we can derive the relations for omega, t and n. How can we write here? For omega square we write g upon r into sin theta upon cos theta. Simply cross multiplying g and r here, but we can substitute for r. R can be equal to L sin theta. L sin theta. Here sin theta upon cos theta. Here sin theta gets cancelled. We get right hand side as g upon L cos theta. So this is for omega square. So omega becomes under root g upon L cos theta. This is our equation number 4. So one term we have obtained. Now the second term is period. Also you know the formula for period. It is basic formula. It is like this. T is equal to twice pi upon omega. So here twice pi and omega just we have obtained. It can be like this, twice pi upon under root g upon L cos theta. So the final relation is twice pi under root L cos theta upon g. So this is the expression for period. Suppose it is denoted by equation number 5. Now from T we can write N, because N is the frequency of oscillation and it is the reciprocal of period, is number of revolutions performed by this point mass. It can be written as here N is equal to 1 upon T. T is equal to 1 upon twice pi under root g upon L cos theta. The simple relation for N. This can be equation number 6. Now we have to find the relation for linear velocity, because velocity and linear velocity and angular velocity both are related with each other. We have relation, it is V is equal to R omega. So it can be obtained from equation number 3. It can be like this. Suppose we have sin theta upon cos theta, sin theta upon cos theta, and right side R omega square upon G. We take this equation 3 as it is. Here multiplied by R divided by R. Then we get R square upon R square omega square multiplied by RG. Simply multiplying R, numerator by R and denominator by R, we get like this. So R square omega square is V square, is divided by RG, and sin theta upon cos theta is tan theta. So we get the relation for velocity. Tan theta is equal to V square upon RG. Here easily we write V square is equal to RG tan theta, or V is equal to under root RG tan theta. This is our seventh relation for the uniform circular motion in case of a conical pendulum. So these equations we have to use in MCQs as well as short answer questions. So and in numericals also we can calculate various terms related to the conical pendulum. So here I take one numerical problem which is based on this equation. We have number of equations here. We use some equations for the solution of numerical problem. I can give you the problem on the board. You also try to revise and remind the equations which we have to use. So here in the textbook, in the exercise, there is problem number 17. So I write here the problem. It is a pendulum consisting of a massless string of length 20 centimeter, so this is one quantity, and a tiny bob of mass 100 gram is set up as a conical pendulum. Now Bob performs 75 RPM. Means here frequency is given and the quantities which we have to calculate are kinetic energy and change in potential energy of the system or of the bob, and it is given in the bracket that pi square is equal to 10. If we have to use pi square, then we have to use the value 10. So this is the problem. Conical pendulum, here length is given 20 centimeter. So we can write the solution here. Given values, L is equal to 20 centimeter, means in SI unit we take it as 20 into 10 raised to minus 2 meter. Next value is M, mass 100 gram is given. It can be equal to 100 into 10 raised to minus 3 kilogram, or it is 10 raised to minus 1 kilogram. And another quantity is given. Bob performs 75 RPM. It is given in the description like this. Simple description is given. RPM is revolution per minute, means it definitely represents the frequency. So N can be equal to 75 RPM. In revolution per minute, it is revolution per minute. If it is divided by 60, then it is revolution per second or hertz. It is equal to 5/4 hertz. Now from this data and one value pi square is equal to 10, we have to calculate kinetic energy. How can we calculate kinetic energy? So we have the relation for kinetic energy is kinetic energy for a bob is equal to half mv square. V is the linear velocity, and for linear velocity we have just derived half into m, and v is equal to under root rg tan theta. This is for B, and square can be taken like this. So for the substitution, we must have to know the theta. But here theta is not given in the problem, but some values are given. Those values we can calculate. Theta can be calculated from those values. And the second question is related to change in potential energy. These two points or these two questions we have to solve in this problem. Here we take these steps like this. We have n is equal to 1 upon twice pi under root g upon L cos theta. Because n is given, L is given, g we can take, therefore here we can solve for cos theta. So once we know cos theta, we can find sin theta and tan theta. So squaring on both sides we get n square is equal to 1 upon 4 pi square, and square of this square root is g upon L cos theta. Cos theta can be taken on the left hand side. We get 1 upon 4 pi square. Here g in the numerator, L is as it is here, n square can be taken on the right side, and substitution gives us cos theta is equal to 1 upon 4, and pi square we have to substitute as 10 is given in the problem. G can be taken as 10, and L is 20 into 10 raised to minus 2. N square is 5 by 4 square, means 25 by 16. 16 can be taken in the numerator. Here n is 5 by 4. Therefore n square is 25 by 16. Here 25 is substituted here in the denominator, and denominator of denominator goes in the numerator. So cos theta can be here calculated in this way. Cos theta is equal to 0 gets cancelled. 4 is 16. 4 upon 25, but 10 into 10 is to minus 2 becomes 10 is to minus 1. It becomes here 40 upon 25. And here again 2 is there, so it becomes 20 upon 25, and easily we can write here cos theta is equal to 0.8. Now here theta, simply we have to write cos theta sin theta. So once we know cos theta, so suppose here I draw the diagram again. This is theta. Cos theta is 0.8, means this side is 8, this one is 10, therefore this side must be 6. So therefore we write sin theta is equal to 0.6, means 6 upon 10. And from that also we write tan theta can be equal to 6 by 8. This is the tan theta. So once we know such values of trigonometric ratios, we can solve for kinetic energy, because this term kinetic energy involves so many trigonometric ratios. Two trigonometric ratios here. So the first point of kinetic energy can be half into m into Rg tan theta square. So here we write Rg tan theta, square of square root. It is Rg tan theta in the square root, and its square becomes Rg tan theta. here half into m. R is, we know R is the L sin theta. R is equal to L sin theta. We can write here L sin theta, G as it is, and tan theta, here it is multiplying. Now substitution gives us, here is half into 10 raised to minus 1 is the mass. L is 20 into 10 raised to minus 2. Sin theta is 0.6. Just we have shown from the geometry of figure. Is sin theta. G is 10 and tan theta is 6 by 8. This can be obtained by considering the simple multiplication here. It is 20 divided by 2 is 10. Here 10 is to minus 1, 10 cancels. Here 0.6 into 10 is to minus 2 into 10, it is 10 is to minus 1, so 6 by 8. So here it is 3.6 upon 8 multiplied by 10 is to minus 1. It can be equal to 0.36 divided by 8 and it is equal to, so here 0, then 8 into 4 32 and then 2 is the remainder here, we get 0.045 joule is the kinetic energy. Now the next segment of the problem is change in potential energy. This is also we have to use from the basics of 11th. It is change in potential energy. It can be obtained this way. So for that also we have to consider the basic like this. Suppose this is the ball, it is at certain position, that position is from the ground, this position of bob is at a height h, then at this position the potential energy is mgh. It is first potential energy or initial potential energy. Now if the bob performs circular motion, then it goes at this position. At this position the potential energy is denoted by 2, potential energy 2, and it is equal to, suppose this much distance for which the horizontal plane is raised is x, then that potential energy can be mg x plus h. So try to understand here the equation of potential energy. Initially it is at a certain height h, it is initial potential energy, it is simply mgh. Now when the particle performs circular motion, it gets slightly raised. Suppose it raises through a distance x, then new potential energy is mg into x, is this h is replaced by x plus h. So change in potential energy can be written as delta PE. It is equal to potential energy in final potential energy minus initial potential energy. It is mg x plus h minus mgh, and it is equal to mgx. mgh minus mgh gets cancelled, we get it is mgx. Here x can be shown here, this distance we have shown by L cos theta. In our derivation, this AC we have shown by L cos theta. And the original length of pendulum, if it is not vibrated, if it is not revolved, then original length means the point or point mass or bob is at a position h from ground. This length is L. Therefore, x becomes L minus L cos theta. So, original length minus the length of axis around which the cone is traced is L cos theta. Therefore, x becomes L minus L cos theta. So, here we write mg inside the bracket L minus L cos theta is mg L 1 minus cos theta. It is the change in potential energy. Now, it can be calculated as by the substitution. The m is 10 raised to minus 1 kilogram, g is 10, L is given 20 centimeter, means 20 into 10 raised to minus 2, 1 minus cos theta is 0.8, simple 10 raised to minus 1, 10 raised to minus plus 1, here the power comes out to be 2 into 10 raised to minus 1, here this 10 into 10 raised to minus 1, and here 2 into 10 raised to minus 2, it becomes 10 raised to minus 1, and inside the bracket it is 0.2. So we get the potential energy as 0.4 into 10 raised to minus 1 or 0.04 joule. So this is the change in potential energy. Calculations are simple, but you have to revise the concept of potential energy. Just again I here try to explain like this. When the bob is not performing UCM, its position is shown at this point and at a height h from ground, then its potential energy is mgh. It is initial potential energy. It is denoted by potential energy 1. But when it performs circular motion, then it gets slightly raised through a distance x. Then at this point, the potential energy is denoted by potential energy 2 and its formula is mgx plus h. So if we take the difference, potential energy 2 minus potential energy 1 means final potential energy minus initial potential energy, we get mg into x, is called as change in potential energy, and the substitution is simple here. But x also you have to understand. X means this distance through which the bob is raised for the horizontal plane. It is from the geometry of our conical pendulum. Original length is L and we have taken the length AC. It is L cos theta. Therefore, x becomes L minus L cos theta. Simple substitution gives us the change in potential energy delta PE is equal to 0.04 joule. This is the second step of this or second question in the problem, and in the first problem we have asked kinetic energy. This is the first and this is the second answer. Kinetic energy we have found simply by half mv square. It is 0.045 joule. So this is about the problem discussion of conical pendulum, and theory also simple to understand. So today we stop here. You can solve the numericals related to conical pendulum as well as you can write the short answer question from the textbook. Thank you.